Okay. Hello guys, this is your second supplement under section 14.3. So in this supplement, we're going to do two things. The first is a proof of the Leibniz rule, which I assume that you guys have already learned at this one, but let's just prove it as a maybe a preliminary or a foreshadowing of our fundamental theorem calculus section, chapter 16. So, and the second point of this portion of the video is to prove the Clairaut theorem, which is the fact that mixed derivatives are the same whenever they are continuous as a function. Okay, so first of all, for a Leibniz rule, let us state this again. It is basically stating that if you have this type of integral, we're integrating some continuous function within some interval given by two functions, a of x and b of x. Then we take the derivative of that function as a function of x. Then you should get this from f of b of x, b prime of x, minus f of a of x, a prime of x. So this is basically directly due to the fundamental theorem of calculus. So let us recall that. There's two parts of the fundamental theorem of calculus. It states that, first of all, whenever f is continuous, you have that this is called an indefinite integral, right? Given an indefinite integral starting whatever point c, then this guy will be an antiderivative of f. So that is basically saying that capital F prime is little f here. And the second statement is that state that you can always evaluate a definite integral via that antiderivative. So f of b minus f of a is always equal to the definite integral of little f from a to b. So those are two parts of the fundamental theorem of calculus that relates between integration and differentiation. So you see that if we now find an antiderivative of this function f, then we can always, by the second part, actually, let me just do that. This is by the second part of the fundamental theorem of calculus, that this guy is basically f of b of x minus f of a of x, right? Now, by chain rule, by the single variable chain rule, you have that this is f prime b of x times b prime of x. And then together, f prime of a of x, a prime of x. Now, by the by the first part of the fundamental theorem of calculus, this kind of thingy is always an antiderivative of f. So capital F prime is f, and capital F prime is f, which we simply get the Leibniz formula throughout these definitions. So yeah, that's basically a proof of this Leibniz rule, and it's in particular, very useful because we will actually see a lot of these examples. Right. Now, for Clairaut's theorem, this proof is kind of fascinating in the sense that we don't really know what we're doing, but we turns out to prove that. So let me state the theorem first. Whenever f is defined in a domain, in this case, it belongs to R2, but you can do the same thing for Rn. And it is a real value function, so it gives a value R. Then, whenever fxy and fyx, obviously they must exist, and they are continuous as a function at the point AB, then we always have that fxy and fyx evaluated at the point AB to be the same. So this is very useful because it'll be very complicated if those two guys are not the same, which we will see soon in, I guess, for section 6 or section 7 when we're dealing with maximum and minimum values. But this is precisely what we want whenever f is nice enough. So let us dig into the proof, which is, as I mentioned, really tricky. And we don't really know what we're doing, but turns out it is we have just proven our theorem. So by definition of fxy and fyx being continuous at AB, we have this following definitions. Given any epsilon, you can always find fxy and fxy xy and fxy AB within distance epsilon over 2, provided that xy and AB are of distance less than delta. And the same thing works for yx. So you can see that is all the way, all of my proof on the absolute data method, I always fix that parameter first, as in the proof of the arithmetic of limit in the previous supplement. Right. Now let us define a strange function, dhk. So d of hk with variable h and k is defined as this: f of a plus h, comma, b plus k minus f of a plus hb minus f of ab plus k plus f of ab. So we define that through a small regime, which is h squared plus k squared less than delta. The delta is given here. So we are trying to understand the difference of the function f within a small region of AB. Okay, now why is this function useful? We will prove the following claim that fxyab, which is the quantity that we desire to know, is actually a limit of hk going to 0, 0 for dhk divided by hk. And that will also be equal to fyx. So through this intermediate term, we can show that these two guys are the same, right? So let's start the proof. Let us first define a small portion of D to be capital F. Capital F is defined to be f of x b plus k minus f of xb. So you can check the definition that actually dhk is given by a difference of capital F. So you see that if you are plugging a plus h, you will get a plus h and b plus k, which is the first term. And a plus hb gives this term. And if you plug a, you get this term and this term. So we have reduced the 4-term problem into a 2-term problem. Now we applied the power forming value theorem. So I would recommend you guys to go back to your textbook to see what this means. Basically, it is saying that if f is a differentiable function and f prime is continuous, then fb minus fa is always equal to some c, f prime c b minus a, where c always belongs to the interval ab. So graphically, it is saying that if you have a function, then by connecting two point, this slope is always the same as some tangent line within that interval. This is in particular very useful. Let us see how this is applicable. First of all, you can apply the mean value theorem to f because it is differentiable, first of all, because the differentiation is simply the partial differentiation of f, of little f, right? Moreover, the differential is continuous. Fx is actually continuous due to the fact that we already assume that fxy is continuous, right? So, yeah, basically we can now apply mean value theorem. So in this case, we have some alpha 1. I use 1 for some reason. Let us see that laterwards. So you have alpha 1 between a and a plus h, so that this guy can be written down back into f prime of alpha 1 h. So that is directly what mean value theorem means, right? Now, by evaluating this guy, it is simply fx of alpha 1 b plus k minus fx of alpha 1 b together with a distance h. Now we apply the mean value theorem again, but now with this function, fx alpha 1 y. So alpha 1 is fixed. This is a single variable function y. Now, why is this applicable? Because again, the differentiation of this guy with respect to y is simply the partial derivative fxy, right? And also we assume that fxy is continuous, so you can again apply the mean value theorem to show that this difference is again some partial derivative f together with some alpha 1 b beta 1, where beta 1 is some number between b and b plus k. So combining these two guys, we have in fact that d of hk, which is defined to be this guy, which reduced to this guy, which reduced to this guy, gives us fxy alpha 1 beta 1 and hk. So we see that if we want to subtract the distance between these two guys, then dhk is simply f of xy alpha 1 beta 1. So you get this guy, fxy alpha 1 beta 1. But this guy is always less than epsilon. Why is that? It is due to the fact that h squared plus k squared is less than delta, and alpha 1 is within a and a plus h, beta 1 is within b and b plus k, so that the point alpha 1 beta 1 is always within distance of delta with ab. But by definition, that is saying that the limit of dhk over hk is fxyab, right? So we now have proved the first claim, which is this side of equality. And you might guess that the other side is just a symmetrical argument, which is precisely true. So in this case, we evaluate y first. We set g of y to be f of a plus h y minus f a y. which you can get the same type of representation that d of hk is given by g of b plus k minus g of b. Again, I strongly encourage you to go back to a definition of dhk and try to show that this is true. And so, yeah, by the same argument, we apply a mean value theorem to G in a variable y, which you get again. D of hk is G prime of beta 2, where beta 2 is again some variable between b and b plus k. And that by definition, G prime of beta 2 is simply the partial differentials of this f respect to y evaluated at beta 2. And a similar argument gives that if you evaluate these two guys using the mean value theorem again, you get fyx, alpha 2, beta 2. Where alpha 2 is again some variable between a and a plus h. So at the end of the day, we have dhk again equal to fyx, alpha 2, beta 2. With the exactly same argument, you see that the distance between fyx and b together with this quotient will be less than epsilon whenever AB and alpha 2 beta 2 are of distance delta. So we conclude the right-hand side equality. The limit of dhk over hk is also the same as fyxab. So fortunately, this is actually true. So via an intermediate step of this limit, we see that these two guys are true. And we see that the existence of the continuity is actually really important for us to apply the mean value theorem. Not only you have to be differentiable in one variable, you also have to be continuous after differentiation. That's the point. So let's recall again that fxy, fyx must both be continuous at a point to show that you have the same quantity of the mixed derivatives. Yeah, so basically that is what we have, the proof of Clairaut's theorem. I might be going a bit too fast, but the details are written down in this proof, so you can sort of read it after you try to understand what I'm saying in this video. But yeah, this is a really, really nice proof. It is obviously one of the first not trivial proof that you guys have encountered in this course, which again, this is not of the scope of our course, but I truly wish you guys can understand how this works and why is the limit and continuity problem so delicate that we have to invent such notation for us to quantify the limit behavior. So everything can be precise and rigorous. Right, so in this proof video, I proved the Leibniz rule and the Clairaut theorem. And you can see that with some example I think in our original video, 14.3, that Clairaut theorem actually fails whenever you don't have the continuity of fxy and fyx. So I encourage you to understand that example to show that it is not really trivial that these two guys are the same. Okay, I guess I will see you in the next video, which should be 14.4, the differentiability of a function. See you guys.